Water of crystallization probably looks like a horrific topic, but the maths in it isn't actually that complicated. This is why it's one of the fundamental core skills we're putting at this beginning of this playlist, where we go through all of the maths you need for your A-level chemistry. So we're going to take you through how to do some really basic questions on this, explaining to you the chemistry, how to do the maths, how to do the algebra that is involved in this. If you do struggle with algebra, please go and watch the previous video where we take you through just the pure algebra skills you need for this. And then once you've got the hang of it, you can go and watch some videos later on in this playlist where we're going to be incorporating this skill into larger exam style questions.
Let's have a look at these questions on water of crystallization. And before we do them, let's just remind ourselves of what water of crystallization is. So remember, water of crystallization refers to the water that can be present within the structure of a crystal. And we might hear of things such as a hydrated salt or hydrated compound, which is a compound that does have waters of crystallization. And then you can also get anhydrous compounds or anhydrous salts, which have no waters within their structure. And generally speaking, you can go back and forth between them. So you can heat dehydrated salt to remove the waters and it will become an anhydrous salt. Well, let's have a little look here at some of these questions and see if we can put that into practice. So, starting with question 1. So here we know the MR of hydrated copper sulfate. So copper sulfate is of course CuSO4.XH2O because this is the hydrated form of the salt. Now what we can do is we can work out what the MR is of just the copper sulfate. So we'd do this in the normal way by consulting the periodic table. So that would be 63.5 for the copper plus 32.1 plus 4 times 16, which gives us an MR of 159.6. Now if we think about it, if we took the hydrated salt and we removed from that the anhydrous salt, so just the copper sulfate bit, we'd be left with just the waters of crystallization, the XH2O. So if we think about that using the numbers that we have, we end up getting the MR of this XH2O, and we see that that gives us 72. So we know now then that the MR of the XH2O is 72. We also know that the MR of just one H2O, just regular H2O, is 18. So we can see how many of these waters there are in this crystal by taking the 72 and dividing it by the 18. And that gives us 4. So in this case, X, the number of waters of crystallization, is equal to 4. So next up, we're told that we have a 13.5 gram sample of hydrated calcium carbonate. And we're told that we heat it until it has a mass of 8.6 grams. Now what that means is that we've removed all of the water from there, and then we're just left with an anhydrous salt with a mass of 8.6 grams. So there we can assume that we can find the mass of water that has been removed by subtracting those two from each other. So let us put some of this into practice then by having a go at this question. So in this case here, we know that we have calcium carbonate, a hydrated version of it. So CaCO3.XH2O. And we know that if we were to heat this, this would become just calcium carbonate plus XH2O because we would remove those waters of crystallization. So if we think about this in terms of the conservation of mass in a reaction, and we subtract the 8.6 from the 13.5, we get the mass of water. And we can see there that's 4.9 grams. So we can think of this in a similar way to how we did empirical formulas. And if we write a little table out with calcium carbonate and XH2O along the top, and then we start now by filling in the rows we write down the mass of each of those two substances, and then we work out and write down the MRs of those substances, both the calcium carbonate and the water. Now what we can do is we can calculate the moles of them. So for the calcium carbonate, I make it that we have 0.086 moles. And for the water, I get 0.272. Now, if we try to get this in terms of its simplest whole number ratio, very similar to when we did empirical formulas, we can divide by the smallest and find this. So if I divide each of these numbers by 0.086, I end up getting 1 for the calcium carbonate, and then I get 3.16 for the water, so a number just above 3. So for that reason, it's quite close to 3. We could likely round that down to 3. And then now that we have that, we can write down the formula of the hydrated calcium carbonate. It's going to be CaCO3.3H2O. Perfect. So let's have a look here at question 3. So here we know that we have hydrated cobalt nitrate, and we're going to heat it up until it reaches a constant mass, which means that we're going to remove the water, leaving us with cobalt nitrate plus the XH2O. So by doing this then, and using this fact of the fact that we have 3.01 grams of cobalt nitrate and we have 0.69 grams of water, we can then use that to work out the mass of the anhydrous cobalt nitrate. And we can get that by simply subtracting 0.69, so the water, from the 3.01, the hydrated cobalt nitrate. So what that gives us is an answer of 2.32, which is the mass that we have of the cobalt nitrate. So what I would recommend that we do now is to treat this a lot like an empirical formula question, and to draw up a little table with the cobalt nitrate and the XH2O, and to fill in a few rows that have the mass of those substances, the MRs, and then the moles. So we know we have 2.32 grams of cobalt nitrate, and we know we have 0.69 grams of water. So the MR we can work out of each of those. So if we were to work out the MR of the cobalt nitrate, that's 182.9, and for water is 18. So we can work out the moles now. And the moles, of course, we're going to do by working out the mass divided by the MR of each of those. And I get here that the moles are 0.0127 for the cobalt nitrate and 0.0381 for the XH2Os. So now we need to get the simplest whole number ratio. We can do that by dividing by the smallest of those. So then I get a 1 to 3 ratio when I divide each of those by the smallest of those, which is the 0.0127. So from that, I can see that X, the amount of waters of crystallization, is going to be 3. And so that there is our solution. So finally here, let's have a go at question 4. And for this one, we're given the MR of the hydrated salt, and we're asked to find the number of waters of crystallization. So to do this here, let's first make a note that the MR of FeCO3.XH2O is equal to 187.8. So if we think, well, what is the MR of just the FeCO3? So in that case, it's going to be 55.8 plus 12 from the carbon plus 3 times 16. And if we tally that all up together, we end up getting an answer equal to 115.8. So if the whole hydrated salt is 187.8, if we were to take away the FeCO3 from that, we'll be left with just the MR of the XH2O. So if we do 187.8 minus 115.8, we'll end up getting 72. And that number corresponds to the MR of the waters in that formula. Well, we also know the MR of just one water is 18. So if we ask ourselves, well, how many of these 18s, how many waters will fit into 72? We will be able to find the number of waters of crystallization. So if we do 72 divided by 18, we end up getting 4. And so 4 will be X, the number of waters of crystallizations in this question.
Ouch! This is why in some videos I'll explain scratches.